Integration by substitution, part 2. Now we're going to do some definite integration, plus another technique along the way. There we are. We've done that sort before, but now we have the integral from 1 to 4. So we're going to do our substitution, u equals du by dx equals du equals. And we're going to write it with a 2x dx at the end instead of dx, and we need to balance, so we still really have x, so there's the half. Now, those are x values. When we change from x to u, we need to replace those with u values. So we use this relationship, the fact that u equals x squared minus 1. So therefore, u equals 4 squared minus 1, u equals 1 squared minus 1. There we are, and we have 15 and 0. And we don't need to substitute back at the end because we are finding a numeric value which we can do sticking to u. Now that isn't a standard integral, and you might wonder, well, why is it by substitution? Well, the only way we can work that is to actually change to sine over cos. Remember one of the fundamental identities in trigonometry, that's tan of x is sine x over cos x. Now that there is a substitution because, of course, the derivative of the denominator is negative sine, so we're just about there. So u equals cos of x, du by dx, negative sine x, du negative sine x. So we're now going to change that to the form where we have negative sine x dx at the end. So there are negative sine x dx. The sine was there, but the negative wasn't there. So we put a negative there, so it's still really the same as that. Now we can do our substitution, but remember that when we substitute, we need to deal with these numbers there and there. So u equals cos of x, so u equals cos of pi by 3, which is a half, and u equals cos of pi by 6, which is root 3 over 2. Now a little note here that the negative of this is the positive of, and I've switched those numbers around. In other words, I'm saying the integral of f of x from a to b is the same as the negative of the integral of f of x from b to a. Here's the reasoning here. Remember back to fundamental theorem of calculus, we talked about the uppercase f of x as being the integral of f. So the integral from a to b is upper f of b minus upper f of a. The integral from b to a is upper integral of a minus upper integral of b. And we put a negative outside, and these are equal to one another. So that's the reasoning why we can just change the sign and swap those numbers. Ln of a minus ln of b is ln of a divided by b by log rules, which is ln of a times the inverse of b. This is a very interesting substitution here. It doesn't look like a normal substitution. If you have a look at this, the derivative of 1 minus x squared is minus 2x. There's no x sitting up there. If there's an x sitting up there, it will be pretty straightforward. So that's not the case. In integration by substitution, we often do very clever trigonometric integrations. If you think trigonometry, then look at 1 minus x squared. Hopefully you think of 1 minus sine squared or 1 minus cos squared. 1 minus sine squared is cos squared, and 1 minus cos squared is sine squared. So I'm going to let x be equal to sine of x, sine of u. Now that's strange because that's the other way around, the opposite direction. Usually we say let u equal, but I'm saying let x equal in this case. But it's still going to work. So I'm going to find dx by du and dx like that. So the difference is, instead of rewriting this so that it matches what du is equal to, I'm going to write cos u du instead of dx. So there we are. Integral from 0 to 1 of 1 over the square root of 1 minus x squared dx is the integral 1 over 1 minus the square root 1 divided by the square root of 1 minus sine squared times cos du. Cos u du, well, that's dx. You see, there's dx and there's dx now. These I need to change. So I'll say, well, x is sine of u, so 1 is sine of u. 1 is sine of u, giving u pi by 2. 0 is sine of u, so therefore 0 is sine of u, giving u as 0. So we now have that integral there. 1 minus sine squared is cos squared. Now square root of cos squared is cos. So we have the integral of 1 du. Which gives us u. We don't need to go back to x because this is definite integration. And we substitute. Very clever. A round switch becomes switch around. We have a process called switch around. This doesn't need it. This is a very simple process. We did this sort in anti-differentiation. Write as two separate terms, simplify, and integrate. And that's finished. But this is a different matter. Here we have a binomial in the denominator. We cannot separate into different fractions, but there is one way around it. Is if we can aim to try to do a substitution which gets rid of the binomial and gives us a monomial, a single term. Well, that's pretty straightforward. Let u equal x plus 4. Which means we have du by dx equal to 1 and du equals dx. But now we have to worry about that x on top, because we can't have an x over u dx. Well, dx we know is du. We have to find what x is equal to. Well, that's pretty straightforward. If u equals x plus 4, x equals u minus 4. So now I can substitute. I'm going to take that u minus 4 instead of x, and u instead of x plus 4, and du instead of dx. Two terms, integrate, substitute back. Now note here, there's a 4, there's a c. 4 and c are both constants, so there's no need to have a 4 plus c. We could just take away the 4 and just have a constant alone. So let's write it as that. If you left it there, I'm sure you wouldn't lose any marks. This we can also do by switch around. I want a monomial in the denominator, so there's my substitution. And I'm going to find du by dx du. Now this 2x minus 3 on top I need to sort out. So we know that x equals u minus 1 all over 3 from that. And therefore 2x minus 3, let's just substitute that into 2x minus 3. And it simplifies to 1/3 to u minus 11. We are now ready to go. There is your top line, there is your bottom line, and du, I need to write that as 3dx. So there we are, 3dx, so therefore a third there, so it's still really dx. And there is our du. Writing as separate terms. Notice the 1/3 has become 1/9 because we wrote 1/3 to u minus 11 there, and the 1/3 jumped to the front, multiplying with the 1/3, giving 1/9. Integrate, substitute back, and we could multiply out the brackets. 4/9 x minus 11/9 ln 2x minus 3 plus c, and that's One there can go because it combines with the c. We can also do this by partial fractions. That'll come up in a later video. You can choose which way to do. Maybe easier by partial fractions. Here's another switch around. We need a monomial, which we can get easily. Let u equal x plus 1. 2x plus 1. That means du by dx du. Now we need to find what 4x is equal to. Well, we know x is equal to u minus 1 over 2. So 4x is equal to 4 times that, which is 2u minus 2. So I have the 4x, I have square root of u, and I just need to create a 2dx, which means I need a half in front. Instead of the half in front, I've separated it out. I've said, well, 2dx, 2 times 2 is 4x, so that's fine. Now be careful of your substitution here though, because I have 4x equals 2x minus 2. Now that's 2x. So I need to put half of that on top. So there is half of 2x minus 2, u minus 1, square root of u. Separate, integrate, substitute back. Here are some exercises for you to try. There's our first substitution. Du by dx equals du equals. So we can write it in the form so we have 3x squared dx. It's 5x squared, so to have 5x squared still I need a 5 over 3. Now remember I have to deal with those numbers there too. So I substitute, there's du, there is 1 over u, and u is equal to x cubed minus 2. So 5 cubed minus 2, 123, 2 cubed minus 2, 6. U equals, so we have du by dx, and u is 2x dx. So we write it with the 2x dx, and that's why we have the half there. Now we need to substitute these numbers to go for the next line. So 0 squared plus 1, so we'll end up with a 1 there and a 10 there. Yes, sine, the derivative of cos. So substitution, u equals cos. We have it in the form where we have minus sine x dx, so therefore there's a negative there. Now we have to deal with the 0 and the pi. U equals cos of x, so therefore we need cos of 0, cos of pi. Cos of 0 is 1, cos of pi is negative 1. And I've done the switch around. You see here, instead of having negative 1, 1, I have 1, negative 1, and I've changed the sign. Now it becomes 0. You'll see why when we do areas under curves. So sec squared is the derivative of tan, so definitely a substitution. So du equals sec squared dx. So that's fine as it is there. Now we need to do our substitution. U equals tan of x, so tan of 0 is 0. Tan of pi by 4 is 1. Here's a switch around. So we let u equal x plus 1. And we have to deal with two things. We need to find du, and we need to find what x minus 1 becomes. So du by dx, so du equals dx, and I need what x minus 1 is. So x minus 1 is u minus 2. So there, x minus 1 becomes u minus 2, x plus 1 is u, and dx becomes du because they're equal to one another. Two terms, integrate, substitute back, and then remember 1 plus c can combine to a single constant. This is also can be a switch around. U equal x plus 5. So there's du by dx. And we need to know what 2x is. So 2x is 2u minus 10. We need to sort those out. So u is x plus 5. So negative 1 plus 5, 4. 4 plus 5, 9. 2u minus 10 instead of the 2x. And square root of u below.